another important thing is that the halogen atom, it has lone pair electrons, and this shows resonance. That is why it is going to have a partial double bond character here. So there are two important things to note down while we are studying the chemical properties of haloarenes. The first point is carbon of CX bond is sp2 hybridized. Therefore, CX bond is not as polar, otherwise is less polar than, is less polar than CX bond of haloalkene. Second important point is CX bond in haloarene, CX bond in haloarene has partial double bond character. Therefore, it is difficult to break. Next important point, benzene ring. Benzene ring is an electron rich. Benzene ring is an electron rich. Is electron rich. Okay. There's a question that can be framed from these things, that haloalkene shows SN, but haloarenes shows SE. Why? Simple answers are, please see. CX bond in haloalkene has partial positive charge. Therefore, has partial positive charge. Therefore, the alpha carbon is electron poor, and nucleophile can attack on alpha carbon showing SN, nucleophilic substitution. Now, next point. So we have explained this part. Haloalkene shows SN. Why is that? Now we have to also explain haloarene show SE. Why is that? So for that we write, since haloarene has benzene ring, which is electron rich, therefore it can attack electron poor electrophile and show SE, electrophilic substitution. SE means electrophilic substitution. As we have nucleophilic substitution, and then we have electrophilic substitution. From here, you will write electrophilic substitution of haloarene. Right here. Halogens show halogens are plus M group. Halogens are plus M group and shows resonance. It shows resonance, which increases the electron density. At ortho and para position. Therefore, haloarenes give ortho para product. Okay. So guys, please see here. I'm going to link the resonating structures. Okay. See here very carefully. Those who have a bit of problem in drawing resonating structures, this is going to be quite helpful. We have halogen atom. This halogen atom will have lone pair, lone pair, and lone pair. This lone pair will move here, and this pi bond will move here. Okay. So whenever you have this type of fragment, some double bond bonded to a single bond, and then that atom is having lone pair electron, that is going to show resonance. The next resonating structure will look something like this. Since the carbon and halogen, it already had one bond, it is making a double bond. This halogen atom is here, and this pi bonds are as it is. This pi bond here, it breaks and it has formed a negative charge here. Okay. Now this halogen atom, since it has donated its electron pair for formation of bond, it will get a positive charge. Next, what is going to happen? This electrons, which is negatively charged, it will move here in this bond, and this pi electron will move to make negative charge on the para position. So this double bond X positive is still here. This is a double bond now. This double bond is as it is, and we have a negative charge on this carbon atom. Moving on, this is going to go once again. This negative charge will move here to make a double bond. This double bond will move here to make a negative charge. This double bond X positive is as it is, and here we have negative charge. Okay, and this pi bond is as it is. This pi bond is a new pi bond. Now what is going to happen? This negative charge is going to move here, and this pi bond is going to break, and it is going to neutralize the positive charge on the halogen atom. So here we have X, and here we have double bond. This is a new double bond, and this also is a new double bond. Now, please imagine that all of these electrons are moving from in a single molecule. All of these electrons are moving in a single molecule, and electrons, they have a speed of light. So you won't see all of these different things. Rather, you will see a hybridized and a mixture of this, all of these structures. And that's what actually present when we look at haloarene. That is the hybridized resonance hybrid structure. So how to make resonance hybrid structure and understand the bonding and the partial positive and partial negative charge is that you identify the carbon atoms. Okay, so I have here first carbon. This is my second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. And then we have the halogen bond. Okay. Now, if you look at the carbon halogen bond, first of all, then the carbon halogen bond is single bond in the first structure, double bond, double bond, double bond, and then single bond. So it is sometimes double bond, sometimes it is single bond. That is why I will give it a partial double bond. Now, if I look at the halogen atom, it is neutral here. It is delta positive, delta positive, delta positive, and it is neutral here. So this halogen atom, even though it has lone pair electron, it is having delta positive charge. Okay. Now let's look at the 1 and 2 bond. Carbon number 1, carbon number 2. It is double here, single, single, and single. So it is also going to get partial double bond character. Similar is the case for 2 and 3. It is single here, it is single here, it is double here, it is double here, it is double here. If I look at 3 and 4, double, double, single, single, single. 4 and 5, single, single bond, double bond, and double bond. 5 and 6, double, 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 single, and single. 6, and then again the first carbon atom, it is single, 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 and double. So all of these bonds are having partial double bond character, and that is why we make a ring here. Okay, we make a ring now, that is showing that these are like all of these are what partially, all of these are partial double bond characters. Okay, now let's look at the carbon atom, which is the first carbon atom, and I will look at the charge right. So when I look at the first carbon atom here, this is neutral, here also neutral, here also neutral, here also neutral, and here also neutral. So it is not going to have any charge. When I look at the second carbon atom here, this is having neutral, here it is having negative charge, neutral, neutral, and neutral. So it is having sometimes negative charge. That is why you will give it delta negative on this carbon atom. Then I look again at the third carbon atom. It is neutral, 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 and again neutral. So this will be neutral, obviously. Fourth carbon atom, if I look at it once again, then this fourth carbon atom, it is having neutral, neutral, negative, neutral, and neutral. So it is getting negative charge sometimes. So I will give it a negative charge here. Okay, so delta partially negative charge. Because it is not always negative, it is sometimes, it is one time negative and the rest of the times it is neutral. Similar is the case for the sixth one. You will also give the sixth one delta negative charge. Now, these are known as the ortho position, which are just adjacent to the halogen, and the one which is opposite to halogen, that is known as the para position. Okay, so this red one is ortho, and the blue one that I have made, that is a para position. So please don't understand that always this position is para. Okay, this position is not para. Okay, please understand that this particular carbon atom, it is not para carbon. Para carbon atom have two groups attached. Okay, so if you have one group attached here, now we have this as para, which is opposite to that particular group. Fine. Now, please write this down. Let me know once you're done. Anyone still writing? Anyone still writing? No one is writing. Fine. Now we will look at the reactions. Okay, don't write anything now. Let me just make all the points and then we will write. So we have to make first of all halogenation, nitration, sulfonation, Friedel graph alkylation, Friedel graph acylation. So we have to make 5 reactions here. So, okay. So let me make, don't write this, okay? Please don't write this. Let us suppose we have a halogen atom here, this X2, in the presence of FeCl3 or FeBr3. So if you are using chlorine, we will use FeCl3. If you are using bromine, we are going to use, अच्छा ऐसे लिख लेते हैं इसको, FeX3 कर लीजिए इसको. अभी तो खैर आपको लिखना नहीं है, don't write anything. So here X can be chlorine or bromine. And mostly we do chlorination or bromination here. Now, what are the products we are going to get? We are going to get chlorine in the ortho position and chlorine in the para position. You'll get X halogen atom. Now this X, actually, let me put an X dash here, which shows that here we are going to get X dash. That means if you are having bromine, fluorine, it doesn't matter. But if you are using Cl2, I will get Cl2 in the ortho position and then I will get Cl2 in the para position. Cl2 in the ortho position and Cl2 in Cl in the ortho position and Cl in the para position. Okay, so we are going to get two products. Let me just decrease the size of these two. So these are the two products that I'm going to get. Now let us look at another reagent. Now, next we are going to do nitration. So nitro group will be added. For that, we need concentrated HNO3. And we also need concentrated H2SO4. And it is going to give you ortho nitrohalorine, and it is going to give you para nitrohalorine. So instead of X, you will have NO2 in the ortho position, and you will have NO2 in the para position. Next, we are going to look at sulfonation, and in sulfonation, we are going to use concentrated H2SO4. And when we use concentrated H2SO4, we are going to get HSO3 in the ortho and in the para position. In the ortho position, we are going to get SO3H. And here also we are going to get SO3H. Then we are going to look at alkylation. So in alkylation, you can use any RX and haloalkene and AlCl3. For this, you are going to get R in the ortho position and R in the para position. R group will be attached on the ortho and R group will be attached on the para position. Then at last, we will look at acylation. So in acylation, we use R group, which is bonded to carbon, doubly bonded to oxygen, and then chlorine. And here also you're going to use AlCl3. Now, in this case, you are going to get again two products. And acyl group will be added onto ortho and the para positions. Okay. So instead of in the ortho position, I will get the carbon which is having double bond O. And this carbon will be attached with the R group as it is. So Cl will be here also this carbon atom is as it is, the double bond, oxygen, and then we will have R group. Okay, so first of all, this reaction is known as first reaction. It is known as halogenation. This is nitration. This is sulfonation. This is Friedel-Crafts alkylation. And this is Friedel-Crafts acylation. Friedel-Crafts acylation. You please draw this down. We'll give you, take your time. And please see that what is getting attached where in nitration, what is the reagent, in sulfonation, what is the reagent, and what is getting attached in ortho and para position. In all of the cases, the para position is going to be the major product because we are going to have more space and the attack is very feasible there. Okay. But you have to write both the products. So please try to understand when we have halogenation, we can use Cl2 and we can also use Br2. So when we are using Cl2, we are doing chlorination. When we are using Br2, we are doing bromination. Okay. Then we have nitration, NO2 sulfonation, SO3H alkylation, alkyl group acylation, acyl group. The R C double bond O, and the C double bond O carbon atom which is going to attach on the carbon on the benzene ring at ortho and para position. Write this down. Let me know once you're done. Done everyone? Yes or no, please tell me.
Yes, sir.
Now, again, a series of questions are there. Okay, so I'm like teaching you guys as you are 8th student or 6th class student that I'm giving you questions and answers also because it gets a bit confusing. I will show you how. For example, they will ask you another question which is related to haloarenes. They can ask you the reactivity of haloarenes. Okay. So when I talk about the reactivity of haloarene, then haloarenes are less reactive than benzene towards electrophilic aromatic substitution. Okay, so they are less reactive than benzene. Why is that? So they will ask you haloarenes are less reactive than benzene towards SE. towards electrophilic substitution. Explain. So here you will write haloarenes, they have halogen atom, and halogen atom, they are very electronegative. And since they are very electronegative, they will have a strong minus sign effect. They will pull the electron density from benzene ring, making it less electron dense than benzene. That is why it slows the attack. So you will write here due to main answer is what? Due to minus sign effect. This is the crux point. Okay. If you don't include this, you will not get any marks. But if you include this, you will get complete marks. And also all of these questions will be asked for 1 marks only in the board examination. I don't know about your school, but in the board examination, you can analyze all the papers. Most of the times, each why question, if they're asking a why question, explain why is that, how is that. All of those questions will be only for 1 marks. So try to make your answers as short as possible. And if you also look at the mark schemes of that is given by CBSE board, that okay, fine. If you have this question, then this is the answer. Then you will also see one-liner answers only for why questions. Okay, so due to strong minus I effect, strong minus I effect of halogen atoms, electron density in benzene ring decreases, and this slows, the attack on electrophile. Okay. Now, so another question comes from this question only. Okay, fine. That so you are saying haloarenes, if they are less reactive, then they are deactivating. Then these are deactivating group. And in 11th standard, you must have learned that deactivating group, electron withdrawing groups, they are going to give meta products. So why is haloarenes giving ortho and para products? Another question arises from here. Halogens are strong electron withdrawing group due to minus sign effect. Due to minus sign effect. Okay, asymmetry, sorry. Are strong electron withdrawing group, but they show they give ortho para products, ortho and para products. Why? But they give ortho and para products. Why? Now, the reason is also there in 11th standard. If you have studied it, if you remember it, the answer is very simple. See, the halogens are strong electron withdrawing group. That is because of minus I effect. But they give ortho and para products because of resonance effect. Okay. So you will write first one. You will explain this. Halogens are. Acha, please listen. Instead of halogens, you can also be asked regarding chlorine is a strong electron withdrawing group, but chlorobenzene gives ortho and para product, right? So it is the same question, but I am writing a generalized version so that if they ask about chlorine, fluorine, iodine, or bromine, you can answer it in a similar way. No need to change the answer for that. You will write answer halogen are strong electron withdrawing group due to minus I effect. Due to minus I effect. But since they show resonance and plus M effect, since they show resonance and plus M effect, electron density increases at ortho and para position. Therefore, one more line that is very important, ortho and para position, and then you will write reactivity is controlled by reactivity is controlled by reactivity is controlled by minus I, that means inductive effect, but orientation, that means where the product will be aligned or will be attached, orientation is controlled by resonance. Okay. Now, if you will be surprised that this question was asked in board examination also, and it was asked regarding chlorine. Although chlorine is an electron withdrawing group, yet it is ortho-para directing in electrophilic aromatic substitution reaction, है ना? SE. In ortho and para products data. Why? You know what the answer, the CBSE marking scheme it provided? It says that due to dominating plus R effect. That's it. That means they just mentioned this part. Due to plus M effect. Okay, so that is the most important point here. Why it is showing? Because of plus M effect. You will see only one-liner answers. Okay, phrases, not even like complete answer. They will start from because. Okay, they will not say that halogens have strong electric, but they give ortho parameters because. No, they will directly start the answer because this, due to this is the answer. Is everyone done? Yes or no? Please tell me. So now, see, all of these questions can be a bit confusing. See, this halogens are strong electron withdrawing group, but they give ortho para products. This question. Haloarenes are less reactive than benzene towards electrophilic substitution reaction. Why? This, and also the first question that we had, haloalkene show SN, but haloarene show SEY. Okay, so all of these questions are very similar because they have a similar term, haloarenes and SE, haloarenes and SE. So you may get confused. That is why I have not written in terms of remarks, but I have written it with question and answers, because I saw many of the students, they get confused. When I write remarks and they ask me, sir, haloalkene show SN, but this is a question NCERT, I could not find the answer. And sometimes they write haloalkene show SN, but haloarene show SE. For this, they will write this answer. Due to strong minus I effect of halogen atom, electron density in benzene. This is not the correct answer. Okay. Or they will write this answer. Halogens are strong, but okay, so this may get confusing. That is why please write these questions and answers separately, and please understand each and every question and answer. Okay. After this, you will write nucleophilic substitution of haloarene. First important point is that haloarenes, they don't show nucleophilic substitution reaction at room temperature, and the following reasons. Due to the following reasons. Now, this has another question which people write in this particular part. They will write the reason why haloarene does not show SN. Okay, so they will ask you a question. The question will be, haloarenes don't show SN at room temperature. Why? Please write haloarenes don't show SN at room temperature. At room temperature due to following reasons. Number one, partial double bond on carbon halogen bond, CX, which is difficult to break. Second point, phenyl carbocation is very unstable. Phenyl carbocation is very unstable. Then third point, repulsion between nucleophile and electron-rich benzene ring. Fourth point, carbon-halogen bond is less polar due to sp2 carbon. No. Please understand all of partial. My spelling is wrong. Please correct the partial spelling here. Partial double bond on CH, which is difficult to predict. Now let us analyze these particular reasons. So we have halogen atom here attached with benzene ring. Obviously, this is a very difficult bond to break because it is having partial double. Now let us suppose we break it. Even if you break it, you will get what? Positive charge here. Now this positive charge is attached with sp2, 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 sp2. And sp2 carbon atoms, these are more electronegative. They will pull the electron density, making the partial positive charge even more partial positive. So charge density will increase and it will become very stable and very unstable. So even if you break it, the phenyl carbocation is very unstable. So they will say, okay, fine, don't break it. Now, this happens when you are doing what? When you are doing the SN1. So let us not go towards the SN1 pathway. Let us try doing this in SN2 pathway. So we can try that also. And in what happens in SN2? In SN2, the nucleophile attacks on the alpha carbon. Right? This is the alpha carbon. Here the nucleophile is going to attack. Now, when the nucleophile will come into contact, right? When it will approach the benzene ring, because that particular alpha carbon is on the benzene ring itself. So it has to attack from the back. It cannot come from the front because we have halogen atom, and it cannot not come from the backside also because we have the benzene. Okay. And because of the repulsion here, what is going to happen? It cannot attack here on the alpha carbon. Okay, even though it is having nucleophile is having negative charge electron, and the benzene ring is also having negative charge. So I will say, okay, fine, it cannot attack because benzene is having because why? Benzene is electron rich. But what about this alpha carbon? This alpha carbon, it is attached with halogen atom. So halogen atom should pull electron density from the carbon. So we'll say no, that is also not possible because the alpha carbon here, it is sp2 hybridized, and sp2 hybridized is more electronegative. So this carbon atom and this halogen atom, both are electronegative. So carbon is also pulling electrons, halogen is also pulling electrons. In total, it is almost what? It is almost equal, and that is why this particular CX bond is not very polar. That is why we don't have a good partial positive charge on the carbon atom of haloarenes, the alpha carbon of haloarenes, and that is why the nucleophile is not attracted towards that particular carbon atom. Okay, so I hope all of you understood all the 4 reasons. Yes or no? Please tell me. Step by step. Tell me, guys. Pia, Hafsa, Mariam Khatun. All of you understood the 4 points? Okay, so try to repeat and explaining this point once again after the class. Okay, to yourself, try to explain. In SN, we have to break the CX bond and a nucleophile will come, but that CX bond cannot break. Why? Because we have partial double. Okay. Now, let us see, it cannot, because let us suppose it breaks also. Then we will get a carbocation, which is going to be unstable. We did something and we broke the CX bond, but the phenyl carbocation will be unstable. If I will say, okay, fine, we will not make phenyl carbocation. Let us attack the nucleophile through SN2 backside attack, and then as the nucleophile is forming bond with the alpha carbon, the halogen atom will be leaving. But that can also not happen because nucleophile is going to attack from the backside because it is SN2, and we already have electron-rich benzene ring on the backside of the halogen atom. That is why nucleophile and electron-rich benzene ring will repel each other. So nucleophile cannot attack. We will say, okay, fine. But the alpha carbon, it should have some partial positive charge because it is attached with more electronegative halogen atom. You see, no, it is not having enough partial positive charge because that carbon is also electronegative. It is also pulling the electron. Halogen is pulling electron. It is also pulling the alpha carbon is also pulling the electron. So almost electron is balanced there. That is why we don't have enough partial positive charge for the nucleophile to attack on the alpha carbon. Okay, so you try to understand each and every step. So these are the 4 reasons why SN cannot happen. Now let us see how we can do SN. So haloarenes can show SN in two cases. Okay, in two cases. See, we have all of these four different reasons, and if we eliminate these four different reasons, then it will be easier. It will be easier to do SN reaction. First of all, what we can do, see, nucleophile is not even coming into contact with the benzene ring and alpha carbon here, right? Nucleophile is not coming into contact. Why is that? Because of some reason it is not coming into contact. We don't want to look at the reason now. The reason is there, but the conclusion is that nucleophile is not able to come into contact with benzene ring. So what I will do, I will increase the pressure. If I will increase the pressure, then automatically whatever compound is present in the solution or whatever compound is present in this particular chamber or a container, they are coming closer because pressure is high. And I will then increase the temperature also. Now, if the temperature is very high, the atoms and molecules are moving very randomly, and maybe one time in 100 seconds, a nucleophile and a haloarene will come into contact with each other and then make a product. So what I will do, I will increase the pressure and I will increase the temperature. If nucleophile comes into contact with alpha carbon, SN will happen. So what we will do, we will pressurize it and we will increase the temperature. So one condition is what we can have drastic condition. Drastic condition means at high temperature and high pressure, nucleophile can come into contact with the alpha carbon and then they can do the SN reaction. That is one way of doing this. Another way of doing this is we will decrease the electron density in the benzene ring. What we are going to do, we are going to decrease the electron density in benzene ring. If we have less electron density in the benzene ring, so benzene ring will be less electron rich, and then the nucleophile can attack easily because benzene has become less electron rich, right? So nucleophile can easily attack. Okay, so these are the two ways in which we can do haloarenes. We can do SN in haloarenes. So please write haloarenes show SN on two conditions. Number one is at high temperature and pressure. Number two is, this is known as drastic condition. Number two is placing of electron withdrawing group at ortho or para position. At ortho or para position. Okay, we'll write a remark here. Note. And the note is regarding the meta position. So why not in meta position? What will happen if I add the electron withdrawing group at meta position? So we all know that benzene ring, if I attach anything on the meta position, then it is not going to show the minus M effect. Okay, so the minus M effect or the electron withdrawing effect, it is only shown when we have at ortho and para position, because meta position, it is inactive in the benzene ring. Okay, so we'll write note here, addition of electron withdrawing group on meta position do not improve the stability of carbon ion, because whenever we do electrophilic aromatic substitution, there is a carbon ion formed. Okay, stability of carbon ion as the negative charge is never at meta position. Okay, because meta position is inactive, it does not show anything when we are having meta position on the benzene ring. All of you done? Yes or no? Please tell me. Okay, one question for all of you guys. All of you are there in the class group, right? You are in my group, yes or no? There is a WhatsApp group of boys and girls. So all of you are there, right? Is there anyone who is not added in the group? Please tell me. Priya is here. Okay. All of those who are attending the class, they will be here, right? And other people also. Deborah is here. Yeah, everyone is here. Okay, fine. Okay. So you have to watch a lecture on conversions. Okay, I will give that lecture, but now write the last topic, that is chirality and optical activity. Okay. So first of all, we will deal with the questions that come. So write chirality. What is chirality? So if they ask you whether the compound is chiral or not carbon, you have to just identify one thing. You have to identify if it has chiral carbon. Chiral compounds contain chiral carbon. बोलिए बहुत बढ़िया सर, बहुत ज्यादा आसान बता दिया आपने तो. Chiral तो बताया नहीं, आप बता रहे. Now we have another question. What is chiral carbon? So please see. Carbon attached to 4 different groups are chiral carbon. The carbon is chiral carbon. Okay. For example, if I have CH4, then CH4 is attached to what 4 groups? Tell me, guys. What are the groups that are group of atoms, or what are the atoms attached with carbon atom here? Tell me. See, each and every carbon atom will have how many bond? 4 bond. So those bonds should be with different atoms. Okay. Tell me in CH4, what do we have? Tell me. Bolo. What are the groups attached with carbon in CH4? Rabia, Rabah, Tarif, Mariam, Hafsa, Fia, Deborah. Carbon is attached to? No, man. Carbon is attached to what? Tell me, Hafsa. Carbon is attached to? Hafsa, Deborah, please answer, na?
Hydrogen.
Oh hydrogen only. 4 hydrogens. All of them are same, yes or no? All of them are same, na? Correct? Arey, yes or no?
Yes, sir. Yes, sir.
Let us suppose we have CH2, Cl2. Now in this case, tell me, are 4 groups attached on carbon atom different, or some are same? Are all 4 different? No, right? So this is also not chiral. And what if we have something like this? Br, and then we have Cl, then we have hydrogen, and then we have Br. Now what about this case? Is there anything same? Any of the group it is same? Is anything same here? Yeah, so this will also not be chiral. Okay. Now let us suppose if you have something like this. Not one. All the groups are different, yes or no? Right? All the groups are different. Now, here we have 2 carbon atoms. So this CH3 is not chiral. This carbon atom is chiral. Got it, guys? Yes or no? Please tell me. All of you got this? Yes? Now, please see. Let's look at some more examples. Identify chiral carbon, chiral molecule. When there's a chiral molecule, you just need to identify if a molecule has chiral carbon, it will be chiral. So number 1, you have been given 2 options. Option A, and then you have option B, which is like this. Okay, now please see. You will identify, you have 4 carbon atoms, you will identify identify each carbon, but you have to be careful. ऐसा नहीं कि सब जगह दिखना है, ठीक है? Please see here. First carbon atom here. First carbon atom. This will be having how many hydrogens? Count the hydrogens here. Count the hydrogens. How many hydrogens in the first carbon atom? 3, right? So can this first carbon be chiral? If we have 3 hydrogen here, can it be chiral? Tell me, guys. If it is having 3 hydrogen, then the 3 groups are same, na, for this carbon atom. 3 hydrogens. All the groups are not different. 3 hydrogens means we have 3 groups same. Fia, Hafsa, Mariam, Khatun, Tarif, Rabah, tell me. Got this? Yes or no? Please tell me. Oh ho. Tell me yes or no fast, quickly. Nahi aaya. Yes or no quickly, guys. Deborah, Fia, yes, Hafsa, Mariam. Yes or no? Yes or no? Quickly. Rabah, Rabia. Turn your mic on, all of you guys. Keep your mic
Yes.
on. No, keep your mic. Keep your mic on. Deborah, keep your mic on. Fia, Hafsa, Tarif, Rabah. How many hydrogens in this carbon atom, in the second carbon atom? I mean, how many hydrogens?
2.
2 hydrogens. Can this be chiral?
Yes.
No. This is having 2 same groups. Na? Hydrogens are same. Yes or no? Are you getting my point? Yes or no? Please try to understand. For chiral molecule, we need to have all 4 groups should be different. But in this second carbon atom, we have 2 hydrogens, and both of them are hydrogen same. So this can never be chiral carbon atom. Yes or no? Got this? What about others? Got this now? Now tell me about this one.
Yes.
How many hydrogens here? 3. Can this carbon be chiral?
No.
It can never be chiral because it is already having same groups here. Now what about this carbon atom, the third carbon atom? It is having how many hydrogens? Tell me, guys.
1.
1 hydrogen. Now when we saw 1 hydrogen, you will wait and you will see now what are the groups on this particular carbon atom. I will erase these points. Okay. And here people generally do a mistake that they identify, okay, fine, what are the groups? So they will say, okay, this is carbon atom. It is attached to carbon. This is also carbon. So 2 groups are same. That is why it will not be chiral. No, that is not the right approach. You have to look at the groups. You will circle the groups. How will you circle the groups? You will make a hydrogen first of all. Make a hydrogen first of all. You identify now. Hydrogen. This group is CH3. This group is chlorine. And then this is the group. The complete thing. All of you got this? Yes or no? Please tell me.
Yes, sir.
All of you got this, right? So all of these are different, right? This is CH3 and this is C2H5. And this is chlorine and this is hydrogen. So all of the groups that is attached on this carbon atoms are different. That is why A will be a chiral carbon. This is chiral. Now, look at the second one quickly. Don't write anything. How many hydrogens? Tell me, guys. How many hydrogens? 3. Can it be chiral? Yes or no?
No.
What about here? How many hydrogens?
2.
Can this be chiral?
No.
How many hydrogens here?
2.
No, not chiral, right? This is 2 hydrogens. No. How many hydrogens here? How many hydrogens here?
2.
2. So this also cannot be chiral. Okay. So that is why A is chiral and B is not chiral. Now let us look at another option here. Okay. Now, as you can identify very easily, I have to look at the alpha carbon. If there is a carbon atom which is only attached with carbon, it is not going to be, because it is going to have, obviously it is going to have 2 hydrogens and so on, right? So this is A option, the second one, and the B option is something like this. Now, from the previous question, we can understand that you will now minimize the steps. You identify, just write directly here, alpha carbon, right? How many hydrogens here? How many hydrogens?
1.
1 hydrogen. So this can be chiral. We have to check. This is OH. This is hydrogen. Okay. So 2 different groups. But this group is what? Tell me, guys. This is what group?
C2H5.
C2H5. And what about this one?
C2H5.
C2H5. So we have 2 same groups, right? This C2H5 and this C2H5 is same. So this cannot be chiral.
Sure.
All of you got this? Yes or no? Hafsa, Fia, Mariam Khatun, Rabah, and Rabia.
Yes, sir.
All of you got this?
Sure.
Now, listen here. We have to identify the alpha carbon. How many hydrogens? 1 hydrogen. Now let's look at the groups. Okay, so hydrogen and OH is always the different. See how you have to minimize the steps now. You will not look at OH and hydrogen. You are going to look at the alkyl groups which are attached. So this is alkyl group is what? Tell me guys, this is
CH3.
CH3. And what about this one? This is
C2H5.
C2H5. These are 3 carbon atoms. No? 1, 2, 3. This will be C3H. H how much? C3H. C3H7. Okay, so all of the groups are different, and that's why this is going to be chiral. All of you got this? Yes or no? Please tell me. All of you got this? हाँ जी बताएं, सबको समझ में आ गया ना?
Yes, sir.
बोलो हाँ ठीक है. अब देखिए थोड़ा सा और पोर्शन रह गया है ना, हम आपको बता देते हैं. तो आप I will give you the recordings, I will give you the timestamps and everything in the chat. Okay, so please see what portion is left. Very small portion. Okay, very small portion. Organic conversion. Each and every batch is going to watch the recordings. Organic conversions recording is there for the complete haloalkane chapter. But please have that list. Okay, method of preparation of haloalkane should be there. Chemical properties of haloalkane should be there. Right. Then sheet for name reaction. So whatever name reaction you have learned in haloalkane, you write the name of the reactions only. Then that will be one sheet for the complete organic chemistry portion. Then for alcohol, you will write all the name reactions in alcohol. Okay. And then for all the organic chemistry, you should write haloalkane and write the list of give reason questions. Okay. So these should be present. And after that only you can start organic conversion. I will give you the lecture recording in the WhatsApp group. Now for organic conversions, what you need to have, you need to understand how to draw structure from IUPAC name. If you have been given an IUPAC name, then you should also understand not only IUPAC, but rather common name also. For example, if it is tert butyl chloride, then you will make the tertiary butyl group and then add the chlorine atom. All of these things I have done in the basics of organic chemistry. If you remember, sec butyl chloride, you will make secondary and point of attachment, and then you will add the chlorine group there. Okay. Then this is one thing that you should know. Then you should at least have the sheets of reaction of method of preparation and chemical properties. Right. So these are the two things which should be present with you while you are doing organic conversions. It's going to be very easy. And while in the organic chemistry, organic conversions lecture recording, there is a slight, for one question I have done a mistake. Okay. And that I will also write and send in the group chat. I wrote some other, different reagent. I wrote the opposite reagent. I actually had to go from RCl to ROH. Okay. So I mistakenly wrote here SOCl2. Okay. That is the only mistake in the particular complete video. So this will not be SOCl2, it will be NaOH, and rather it will be aqueous NaOH or aqueous KOH. Okay, so that's one mistake I meant while doing it quickly. I did a mistake at that time. And what portion you have to watch also